Hello, everyone. I'm Palash, and today we'll be reviewing this paper titled as a feedback loop and bipublic amplification recommender systems. This paper was published at CIKM 2020, which is like a reputed conference, which means like the International Conference on Information and Knowledge Management in Ireland. The paper is published by these five authors, and I'm really grateful and thankful to these authors for the important contribution to the field of recommender systems and the uh, algorithmic fairness. Now, this paper sheds light on how recommender systems can silently amplify bias over time, particularly affecting minority groups. And let's understand in this review what they found. Before we move to the next slide, I would like to show which paper I'm talking about exactly. So I'm talking about this paper, like feedback loop and bias amplification, and I'll share the link in the description. This is the PDF for it, and this is something that we'll be reviewing in this video. Cool. So let me start with a simple question while we discuss this about this paper. Like, what happens when Netflix or Amazon keeps recommending the same popular stuff to you? I mean, let's say on Netflix you watch Avengers one evening, and Netflix immediately recommends more Marvel movies. You watch a couple because they're right there on your screen, and now Netflix is convinced you only like superhero movies. Meanwhile, that beautiful Indian movie you would absolutely love, it never shows up on your feed because it's not popular enough. Now, multiply the same experience across millions of users, and you have a system design that has big popularity echo chamber. The popular things get more popular, and everything else slowly disappears. And this is the problem this paper talks about, and this is the problem we are going to explore today. Now, here's the core problem that this paper discusses. Now, recommender systems have what we call a rich get richer problem, technically called as popularity bias. A small number of popular items gets recommended over and over again, while the vast majority of the items are getting ignored. But here's what makes worse. This isn't a one-time problem. The bias feeds back into the system. Users interact with biased recommendations. The system record those interactions as genuine preferences, and then it recommends even more popular item next time. Now, this is like a self-reinforcing loop. The goal of the paper is to formally study this feedback loop effect and measure how it amplifies popularity bias over time. Now, again, like this is not the first time researchers have noticed the long-term effect of bias systems. There have been other papers as well, like a couple of people that I just mentioned in this slide, and I'll share those as well in the description format. And there are such papers we have identified this. This paper explored it from a different perspective, and that's what we'll be discussing. Now, I want to, but I want to discuss the gap. The gap is that no one had formally proven this specifically for recommender systems using real data, and no one had measured which user group got hurt the most. That's what this paper does. This paper does not actually goes to the real data. It uses a predefined MovieLens data, but it definitely identifies which groups get hurt, and that's what we'll be discussing in the upcoming slides. Coming to the research questions and the scope part, there are some questions that this paper actively asks and answers as well. Let's say, does the bias actually get worse over time? Like, and can we mathematically prove it? Second, what breaks because of this? The diversity breaks, the user preferences breaks, or a fairness breaks? The third, who gets hurt the most? Now, what does this paper does while answering these questions? This paper studies the popularity bias amplification through feedback loops. It also measures on the impact on declining aggregate diversity, shifting user taste over time, and the homogenization of user experience. And for now, like, don't worry about any of the word that you don't understand. We'll be discussing each and everything in detail so that it makes sense as we move forward. This paper also shows the minority groups that are hit harder, and the paper demonstrates an experiment where user interactions are done over 20 iterations. And and this paper also demonstrates the three algorithm that was tested on this particular movie data set that we're discussing. The minority group that we're talking about in this case are the female users. They are hit significantly. The data that we have has a majority of male users, and then minority is the female users, and that's how we'll see like how the female users their preferences are also updated in line with the male users, and that's what we'll be checking it out. Now, before we go deeper, let's just make sure that we all are on the same page about what the recommender system actually is. So, in very simple word, it's a system that predicts what items, movies, products a user might like based on their past behavior. Now, let's say you interact with these systems every single day. When Netflix says like, because you watched Breaking Bad, that's a recommender system. When Amazon mentioned that customers who bought also bought these products, that's a recommendation system as well. Spotify has a discover weekly playlist. YouTube's have recommended videos. All these are recommended systems. So this is what recommendation system actually is. And that's the promise that they do. But in reality, there have been instances, and there are instances that these systems have hidden biases. And that's what we'll be discussing in this paper. Moving to the next concept, which is about algorithmic bias, and we'll be discussing about algorithmic bias a lot. So I think it's better that we discuss it right now. So what's an algorithmic bias? It's when an algorithm systematically produces unfair outcomes, favoring certain groups or items over others, not because they are better, but because of how the algo is designed or what the data is trained on. Now, there are several types of algorithmic bias. One is the selection bias. When selection bias occurs when the training data doesn't represent the full population. The next is popularity bias. This is something that we'll discuss in detail, and this happens when the algo favors items that are already popular. The third is the position bias, which means the item shown at the top of a list get more clicks. So let's say if I show you a list of 10 items, you have or the best example is like when you Google something and you get 10 results, the probability of clicking the first one is always the highest. So that's a perfect example of position bias. The last one is the confirmation bias. This happens where system keeps reinforcing existing patterns instead of exploring new possibilities. So it's like you have already decided that this is true and you are finding evidence to confirm your predefined assumption. So that's confirmation bias. So yeah, moving to the next slide, we'll be discussing about popularity bias because this is the crux of the entire paper. Now, this is the tendency, popularity bias, the tendency of the recommender systems to disproportionately recommend popular items while ignoring the vast majority of the catalog. So if you see this long tail distribution, right? Like you'll see what's called as like if you see the long tail distribution, this a tiny fraction of items that had received the overwhelming majority. Like this received the overwhelming majority. Meanwhile, the vast majority of items, the long tail, like this is something which is very rarely recommended. So think of it like 1% of item is getting 80% of the attention. Think of it think of the same example, right, where the Marvel movie is keep getting recommended again and again, when Marvel might be just 1% of the overall Netflix collection that they have. Now, where does this bias come from? Now, there are two sources for this. One is the data itself. Data itself is biased. In any data set, a few items naturally have more rating than others. The second source of the bias is, and this is pretty important, is the recommendation algo doesn't just reflect this bias. It propagates and amplifies. The algo sees that popular items have more data, makes more confident predictions about them, and recommends them more, which makes them even more popular. So it's like a cycle, one after the other. Moving to the next slide, we'll be talking about feedback loop a lot. So what's feedback loop? Now, also the feedback loop is the heart of the paper. So I mean, we will understand how feedback loop works in four very predefined steps. The step one is the algo recommends popular item because it has more data about them and can make more confident predictions. So this is step one. Step two happens when the user interact with those items, not because they love it, not because they like it, but because that's what is shown to them. So the step two is interaction. The third step is system record these interactions as preferences. It doesn't know, the system does not know that a user chose it because they love it or the user chose it because It was the only thing that was shown to them. Step 4 is, I mean, step 4 now, it would be pretty obvious that the algorithm trains on this new data, which it feels is a user preference, and recommends those same items which users saw, even which is now become even more popular in the next iteration. So these are the 4 steps as a part of feedback loop. You can also think it in terms of the analogies, right? Let's say if there is a snowball rolling downhill, the more it rolls, the more snow it connects. The more snow it collects. Sorry. So, and that's how that's the feedback loop. That's how it works as well. The fundamental danger in feedback loop is the system mistakes its own influence for genuine user preference. It created the behavior, then learned from it and thinks that it is organic. And this is feedback loop. So feedback loop, there are multiple perspectives to feedback loop. There are feedback loop is a great thing to have, let's say in terms of neural network and everything. But in kinds of model like this feedback loop is a fundamental danger because the model is learning from its own mistakes and it's not improving on top of it. And that's why feedback loop is not always best for all ML models. And that's what the paper is about. Now, the algorithms tested in this paper are all based on a technique called collaborative filtering. And let me explain what this means in very simple terms. Now, collaborative filtering is a recommendation technique that uses historical interaction data, ratings, clicks, purchases between users and items to generate personalized recommendations. Right now, the core idea is quite simple. Let's say people who agreed in the past will likely agree in the future. So let's say I bought a particular dry fruit from Amazon. There are very high chances that I'll purchase it again if I liked it. Right? Now, there are 2 approaches to collaborative filtering. One is user based. Find users who are similar to you based on the rating patterns, then recommend what they like that you haven't seen yet. This is the people like you also was approach, right? Let's say, and the next thing is the item based. Find items similar to what you've already liked and recommended those, right? So let's say by user base, I mean, let's say I and like person A, person B have both, they are buying product A. Person A also bought product B, and then product B is recommended to person B, right? And the similar thing is like, let's say I bought a new laptop. In that case, a recommendation can be, can you like you can also buy new headphones. So that's like an item-based recommendation. So collaborative filtering are of 2 types. Like now, why this matter? Like why this collaborative filtering and why these 2 types matter to our paper? Because all the algorithms tested here are collaborative filtering methods. We'll discuss about 3 algorithms, and all 3 are collaborative based filtering methods. All those algorithms learn from our user item interaction patterns, and if those interaction patterns are biased, which are, then the algorithm inherits and amplify that bias. Now we discuss the homogenization. What is homogenization? If you see in this slide, right, like if you see the right and the left and the right section. So before feedback, if you see for male users had a preference of action, sci-fi, and thriller, and but female had preferences for drama and romance comedy. After 20 iterations of training and retraining and feedback loops, male users had updated the preference of action, sci-fi, and popular drama, while female users had preference of action, popular drama, and romance. Now, preferences, if you see, like the preferences might have converged now, no, and individuality has been erased, right? Unless and until they have specific details about if the user is male or female, like individuality has quite been erased, and this is homogenization. Like, there's no individualistic pattern for different categories. Now, moving to the paper details. Now, this data that the people used, that the researchers used, the MovieLens data. There are 6,000 users in this data, 3,700 movies, total ratings close to 1 million. Rating scale is 1 to 5. Data set density is 4.4, and there are 18 unique genres. Now, the most important thing, the gender split. The male we have 4,300, female we have 7,300, 1,700, and this is quite imbalanced. Males provide 3x more data. Again, popular items reflect male preferences. Now, here's what's critical for the fairness analysis. Right? Let's say there are 4,300 male providing about 754,000 ratings, and only 1,700 females providing about 246,000 ratings. Males make up about 72% of the user base. The imbalance is very important because it means the popular items in this dataset are disproportionately shaped by male preferences. That's why the recommendation by system is essentially pushing male dominated preferences on the female users as well. I hope this makes sense. Now, what are the three algorithms that we are testing? Like the first is UserKNN, user-based K-nearest algorithm. This is like a very classic collaborative filtering approach. It finds the 50 users most similar to you based on rating patterns, then recommends items they like that you haven't seen yet. It works on explicit rating, the actual 1 to 5 scores. The second is BPR. BPR stands for Bayesian Personalized Ranking. This is a more modern approach based on matrix factorization. And instead of predicting exact ratings, it learns to rank items, figuring out what you would prefer over what you wouldn't. Now, it works with binary data, just whether you interact with something or not. The third is the most popular algorithm. I mean, the name of the algorithm is most popular. This is the very simplest possible baseline that we can have. And this algorithm, it just recommends whatever is most popular that we haven't seen it. This does not have any personalization. This serves as the worst case scenario because it has maximum popularity bias by design. Now, there's no reasoning mentioned of why the author selected these three algorithms, but my understanding is that these three algorithms they will give us a spectrum from a classic personalized method, which is UserKNN, to a modern ranking method, um, which is BPR, and to a non-personalized baseline, which is the most popular algorithm, the third one. If the feedback loop effect shows up across all three, we know it's a fundamental problem, not specific to one algorithm. So the research that is being done as a part of this paper uh, tries to emphasize that at the end we'll see that the bias that is being inherited is applicable on all the algorithms, not just one. And that's why probably these three algorithms were selected. Now let's understand how the researchers actually tested it, because they don't have access to a live platform like Netflix. They designed an offline simulation based on the MovieLens data. The simulation mimics how users interact with a recommender system over time. Now, this simulation ran for 20 iterations. In each iteration, this is what happened, the 6 steps that you see. The step one is about splitting data into 80% for training and 20% for testing. Step two is about the recommendation model on training data. Step three is generate recommendation list for all the users. Step four is simulate which items users would actually click on. Step five is the estimate what ratings user would give those items. And the step six is add these new interactions to user profile, thereby creating the updated data for the next iteration. And then the loop repeats. Like we have 20 such iterations. So we have 20 such loops. And this is the feedback loop in action. Right now, three important design choices that happen. First, users are more likely to click items ranked higher in the list, obviously, right? Like this follows what's called exponential decay. Exponential decay, let me just show it to you quickly. Uh, this is, I was just searching it. So this is exponential decay. See, like, so there's a sudden fall after it, right? So that's why like people are very highly likely to rate what's on the top, and then they don't want to move to the next set of positionings. Sorry, getting back to the PPT. Yeah. Yeah, so that's the first design choice, right? The item at rank one, the very first thing you see has about 95% chance of being cleared. Uh, now, the second design choice that we have is like if an item is already in a user's profile, it won't be added again. You don't rewatch the same movie, right? And the third design choice is time here. The time that we see here doesn't mean calendar days. It means consecutive rounds of interaction. So When we say 20, it doesn't mean the 20 days or 20 weeks. It means every round of interaction. So these are the three design choices. Now we'll deep dive. Let's just walk you through it, through the technical component of the simulation in detail. And even if you don't understand the technicality, it's completely fine. We will eventually understand the subjectivity of the paper as well. So this is only for reference. If you're not interested, feel free to skip the next two slides and we'll be good. Yeah. So let's just walk you through to the two technical components of the simulation. There are two parts to it. The part A, how do we simulate which item a user clicked? Right? Like they use an acceptance probability formula, and let me just break it down to piece by piece. The probability of clicking item I equals e raised to the power of alpha times the item's rank. Now, e is just a mathematical constant, approximately like e equals to 2.718 is the base of the natural log. Alpha is the negative number, let's say minus 0.05, and think of it as a decay rate, right? That controls how quickly the probability drops. And rank is simply the item position in the list. 1 means it's the first thing shown. 50 means it's at the bottom. Right? I'm talking about this part. Rank 1 is the first thing shown, and the rank 50, it's at the very bottom. So higher the rank, more likely to click. Right now, here's the key insight. Because the alpha is negative, we mentioned, right? Like alpha, let's consider alpha, this is the alpha. Alpha is minus 0.05. Because alpha is negative, as rank increases, alpha times rank becomes a larger number. And e raised to a larger negative number is very close to 0. So for rank 1, we get e to the power of negative 0.05, which is about 0.95, which is a very high probability. And if the rank is 50, we get e to the power minus 2.5, which is about 0.08, almost 0 probability. This is exponential decay that we just Googled as well, right? The probability doesn't decrease in a straight line. Coming to the part B, once a user clicks on an item, what rating would they give? They use item response theory. The formula has three components added together. First, the user's average rating. This captures how generous or harsh a rater this person is. Someone who averages 4.2 stars is generous. Someone who averages at a 2.8 star is quite harsh. Second is the user's rating spread multiplied by the item's average rating. This captures the interaction with how the variable this user is and how well received the item is. A user with high variable rating, a well-loved item, will likely rate it high. The third part of this formula is the random noise from a normal distribution. This adds very realistic unpredictability because human ain't perfectly consistent, right? Like you might rate the same movie differently on different days. Finally, we round off everything. You see the final rating is rounded off, but we round the result to get an integer and clip it to 1 through 5, like because we only want to have natural numbers from 1 to 5 for the ease of discussion and the calculations as well. If it gives 5.7, it gets clipped to 5. If it gives 0.2, it gets clipped to 0. The result is a natural number rating that gets added to the user profile. And this completes one cycle of feedback loop. I hope the part A and part B is clear. Now, here's the most elegant part of the paper. Again, if you are not interested in the mathematics part, you can skip this slide as well, and after that, it will be our very subjective discussion. So the most elegant part of the paper is like they don't just show the bias increase empirically; they prove it mathematically as well. And let me just walk you through this step by step. Step one: the starting observation. At any iteration T, the average popularity of recommended items is proportional to average popularity of the data set plus some extra amount theta. Now, what is theta? It's the extra popularity boost that the recommendation algo adds up. And here's the crucial insight: theta is always positive. Why? Because recommendation algo, by their very nature, tend to recommend items that are more popular than the average item in the data set. And that's the whole popularity bias, right? Like you will also recommend items which are more popular than the average item in your entire list. So step one means that the algorithm favor popular items. Coming to step two, which is after users interact and how the data gets updated, what happens when users interact with these recommendations and those interactions get added back? The new average popularity of the dataset equals the old average popularity plus a fraction. Why? Because that fraction is k times theta divided by the dataset size. K is the number of new interactions added, one per user per iteration. Step three, here's the proof, like the exact proof, like why does bias always grows. Look at that added fraction carefully. You see this? Sorry. Yeah. If you see this added fraction carefully, it K is a positive because users always click something. Theta is positive because the recommendations are always more popular than the underlying data. The denominator, data set size plus K, I mean, this is this is data set size plus K. It is positive because you can't have a negative data set size, right? Like, so we have positive times positive divided by positive, which equals positive always, and no exception. And that's why the bias keeps growing, right? So, I mean, I found this is the most elegant part of the entire paper. Moving to the next slide, this is and now we'll be discussing results. We are done with the technicalities, the methodologies, and everything. These are the results we'll be discussing. Now, if you see this is the first result. This graph shows the average popularity of recommended items across 20 iterations. So if you see, the average popularity is increasing for all three algorithms and for all 20 iterations. Most popular, the most popular algorithm shown in green starts at about 0.26, which makes sense because it always recommends popular items. It climbs to 0.39. Similarly, UserKNN, which is in blue, starts about 0.15, increases up to 0.22. This is, again, just to remind you, UserKNN is personalized. So it doesn't start as bias, but the feedback loop still pushes upward. BPR, this is the most interesting part, the one in the red. It started at the lowest at about 0.05, but it had the steepest relative growth. Like it's increasing by 4x almost, right? By we reach iteration 20. The authors have noted this steep slope, but acknowledge they don't fully understand why BPR amplifies bias so aggressively. The key takeaway is that, and because they have mentioned that they do not fully understand why BPN amplifies, this can be a further area of research. The key takeaway is that all three algo, regardless of their design philosophy, confirm the mathematical proof that bias always grows, popularity always increases, the feedback loop is inescapable without explicit interventions. Now, this is the result too. This is about diversity being collapsing. Now, the flip side, here we saw that here we saw that popularity is increasing of the item that were recommended. Here we see there the diversity collapses. Right now, what happens in diversity? This graph shows that the aggregate diversity, which is the percentage of total movie catalog that appears at least once, it keeps on decreasing. Right, the BPR again, if you see the red one, this has the most dramatic story. Initially started with, let's say, more than 55% of the coverage. By the end of it, it's only having like less than 5% of the coverages. Again, you can see the same thing for UserKNN. It starts about 10 and reaches to about 2, right? Like, but what does this mean practically? Like, this means that if you started Netflix with, let's say, 55 movies, by the end of it, the recommendation has decreased a lot. Initially, you are able to see 55% of the recommendation of the entire Netflix movie. By the end of it, let's say after 20 iteration, after you have watched 20 movies, you might only be seeing only 5% of the Netflix recommendations. So that's how the diversity is collapsing. And that's what this slide wants to say. And that's what also wants to demonstrate. Result 3 that we have, this is about distortion in your taste, distortion in the genre that you like. The author measures how much each user's genre preference profile has shifted from the original preference, and they use a metric called as Kullback-Leibler divergence, or I mean that's simplified, in simple words it's called as KLD. Right, like, now all these algo, if you see, right, like, show increasing deviation from initial preference over time, right? Like UserKNN causes the highest distortion by iteration 20. Now, again, what does distortion means in practice? The system is progressively forgetting what you actually like. Your user profile, which the system uses to make recommendation, become less and less representative of your true preference. Again, why? Because your taste is getting distorted. Coming to the result for everyone starts looking the same, be it male or a female. The next slide will be talking about that category part, but eventually it happened that the KLD between male and female group genre distribution, if you see the KLD group distance for all these three algorithms, that also start looking the same, right? So at the start, so what's happening is that the system is erasing the natural difference between user groups. Male and female users start with genuinely different taste profiles, different genres, but as the feedback loop pushes popular items, um, female profiles start looking more and more like the male profiles. This is what I was talking about. This is quite important as well as a concerning finding because authors split the analysis by gender and find that female users, which is the minority group here, experience 2 to 3 times greater preference distortion than male users. Now, the same observation can be applied to other industries as well. Let's say about the policies made by government. If they are made for the majority of the people, the minority definitely gets impacted. And this is a very straightforward observation because observation is the same you can directly apply to any other industry as well. Now, why does this happen? Males make up to 72% of the users and provide 75% of the ratings. So the popular items in this dataset are disproportionately shaped by male preferences. When system recommend these popular items to everyone, including female users, female profiles start accumulating items that reflect male tastes. Over 20 feedback loops, over 20 iterations, their profile gets pulled further and further from the original preference toward the male dominated patterns. And meanwhile, males barely notice because the popular items already match the resistant taste. And this is the most important and most concerning observation as well from this particular slide. Let me summarize all 5 findings in one go. Popularity bias increases, and it's mathematically guaranteed to grow, as we saw in the previous slides. Aggregate diversity decreases, like BPR collapsed from 55% to just 5%. Taste accuracy decreases. We talked about a distortion in the taste, right? The system progressively forgets what user actually liked. Homogenization increases. Different user groups, majority and minority, converge toward the same average profile. And the most important one, minority impact is disproportionate. Females suffer 2 to 3x more distortion than other categories, than the majority categories. So if you have to summarize the entire paper into one particular line, I would say that small biases today become big problems tomorrow, and they hurt the vulnerable most because again, talking about the minority impact. The strength of this paper, and this is very important thing. Like we have a very elegant formal proof, right? That the mathematically, and why? Because we were mathematically able to prove that bias will always increase. There's a multi-dimensional analysis assessment that has been done in this paper, which shows like what is breaking because of the bias. Diversity is decreasing, taste has been distorted, fairness has been distorted. There's also a fairness lens of this paper, so that reveals the disproportionate impact on the minority group, in this case, the females. The paper is quite practically relevant because we all have been able to relate to Netflix, Amazon, and Spotify examples, and the framework is quite reproducible. The data set, which is it is publicly available. There's a very straightforward methodologies. There are very straightforward 3 direct algorithm that has been used, and we can directly replicate. The last strength is like the very progressive storytelling. Like it builds from proof, then observation, then consequence, and then fairness. Also, the maths is also very straightforward and very easy to understand. Again, like all papers, this paper also has some limitations. Um, first one is the only one data set. They're using only one MovieLens 1 million. Um, we are yet to evaluate the researchers are yet to evaluate if these results would hold for e-commerce recommendations. I'm using streaming as well. It might, but we don't know. Second, there's no statistical rigor in the result. No confidence intervals, no error bars, no repeated trials. So we are looking at a single run trajectory. So this is not bad for a research paper, but something worth exploring in the next steps. Like if someone wants to do a next step on top of this paper, definitely it's a must do. The fourth is like the gender grouping, which is binary and oval simplicity. We only have male or female. So we can have more details. Let's say we could have a geography or other dimensions as well. The one other limitation that I want to discuss about the acceptance probability model, that the users click item with exponential decay by rank. This is assumed but never validated against real click data. And the last one is that they don't test any modern deep learning recommendations. I mean, the 3 algo that the authors use is should be used because it was able to demonstrate the breadth of the algorithm. But there are other deep learning recommenders as well, like the neural collaborative filtering, variational autoencoders, and graph neural networks. And because right now that the field of recommendation system have moved significantly beyond UserKNN and BPR. So definitely as a next step, someone, if they want to extend this research, they can try this on the most advanced deep learning recommendation systems as well. So I think in the previous slide as well, in the limitation part, we discussed the future takeaways and the future possibilities as well. But there are other future directions as well, where like we can also test about some debiasing algorithm, because this paper didn't talk about solutions. How can we solve this problem? So we can definitely try like if the debiasing algorithm, some of it like fair match, like the calibrated recommendations, if they would help. We can also try the deep learning recommenders and improve the grouping, which we discussed again in the limitation slide. And again, the new industry, let's say e-commerce, music, or news. So definitely these are some future possible next steps from this research. Um, and yeah, I mean, this was a paper review from my end. I really enjoyed reading this paper, and thanks to authors for drafting this and publishing this. I think I had a huge learning. So thanks everyone, whoever followed till now. If you have any feedback or question, feel free to share that in comments. Thanks a lot. See you. Thanks. Bye.